Algebra is one of the broad parts of mathematics, together with number theory, geometry and analysis. In its most general form, algebra is the study of symbols and the rules for manipulating symbols and is a unifying thread of all of mathematics. As such, it includes everything from elementary equation solving to the study of abstractions such as groups, rings, and fields. The more basic parts of algebra are called elementary algebra, the more abstract parts are called abstract algebra or modern algebra. Elementary algebra is essential for any study of mathematics, science, or engineering, as well as such applications as medicine and economics. Abstract algebra is a major area in advanced mathematics, studied primarily by professional mathematicians. Much early work in algebra, as the Arabic origin of its name suggests, was done in the Near East, by such mathematicians as Omar Khayyam. Elementary algebra differs from arithmetic in the use of abstractions, such as using letters to stand for numbers that are either unknown or allowed to take on many values. For example, in the letter is unknown, but the law of inverses can be used to discover its value. In the letters and are variables, and the letter is a constant. Algebra gives methods for solving equations and expressing formulas that are much easier than the older method of writing everything out in words. The word algebra is also used in certain specialized ways. A special kind of mathematical object in abstract algebra is called an algebra, and the word is used, for example, in the phrases linear algebra and algebraic topology. A mathematician who does research in algebra is called an algebraist. How to distinguish between different meanings of algebra? For historical reasons, the word algebra has several related meanings in mathematics, as a single word or with qualifiers. Such a situation, where a single word has many meanings in the same area of mathematics, may be confusing. However, the distinction is easier if one recalls that the name of a scientific area is usually singular and without an article, and the name of a specific structure requires an article or the plural. Thus we have, as a single word without article, algebra names a broad part of mathematics. As a single word with article or in plural, algebra denotes a specific mathematical structure. See algebra and algebra over a field. With a qualifier, there is the same distinction. Without article, it means a part of algebra, such as linear algebra, elementary algebra, or abstract algebra. With an article, it means an instance of some abstract structure, like a Lie algebra or an associative algebra. Frequently both meanings exist for the same qualifier, as in the sentence, commutative algebra is the study of commutative rings, which are commutative algebras over the integers. Algebra is a branch of mathematics. Algebra began with computations similar to those of arithmetic, with letters standing for numbers. This allowed proofs of properties that are true no matter which numbers are involved. For example, in the quadratic equation, can be any numbers whatsoever, and the quadratic formula can be used to quickly and easily find the value of the unknown quantity. As it developed, algebra was extended to other non-numerical objects, such as vectors, matrices, and polynomials. Then the structural properties of these non-numerical objects were abstracted to define algebraic structures such as groups, rings, and fields. Before the 16th century, mathematics was divided into only two subfields, arithmetic and geometry. Even though some methods, which had been developed much earlier, may be considered nowadays as algebra, the emergence of algebra and, soon thereafter, of infinitesimal calculus as subfields of mathematics only dates from 16th or 17th century. From the second half of 19th century on, many new fields of mathematics appeared, most of which made use of both arithmetic and geometry, and almost all of which used algebra. Today, algebra has grown until it includes many branches of mathematics, as can be seen in the mathematics subject classification where none of the first-level areas is called algebra. Today algebra includes Section 08 General Algebraic Systems, 12 Field Theory and Polynomials, 13 Commutative Algebra, 15 Linear and Multilinear Algebra. Matrix Theory, 16 Associative Rings and Algebras, 17 Non-Associative Rings and Algebras, 18 Category Theory. Homological Algebra, 19K theory and 20-group theory. Algebra is also used extensively in 11-number theory and 14 algebraic geometry. Etymology. The word algebra comes from the Arabic language from the title of the book al-jebr wal cubed bala by al-Khwarizmi. The word entered the English language during Late Middle English from either Spanish, Italian, or medieval Latin. Algebra originally referred to a surgical procedure, and still is used in that sense in Spanish, while the mathematical meaning was a later development. History. The start of algebra as an area of mathematics may be dated to the end of 16th century, with Frenes section via T.E.'s work. Until the 19th century, algebra consisted essentially of the theory of equations. In the following, Prehistory of Algebra is about the results of the theory of equations that precede the emergence of algebra as an area of mathematics. Prehistory of Algebra. The roots of algebra can be traced to the ancient Babylonians, who developed an advanced arithmetical system with which they were able to do calculations in an algorithmic fashion. The Babylonians developed formulas to calculate solutions for problems typically solved today by using linear equations, quadratic equations, and indeterminate linear equations. By contrast, most Egyptians of this era, as well as Greek and Chinese mathematics in the first millennium BC, usually solved such equations by geometric methods, such as those described in the Rhind mathematical papyrus, Euclid's Elements, and the 9 chapters on the mathematical art. The geometric work of the Greeks, typified in the Elements, provided the framework for generalizing formulae beyond the solution of particular problems into more general systems of stating and solving equations, although this would not be realized until mathematics developed in medieval Islam. By the time of Plato, Greek mathematics had undergone a drastic change. The Greeks created a geometric algebra where terms were represented by sides of geometric objects, usually lines, that had letters associated with them. Diophantus was an Alexandrian Greek mathematician and the author of a series of books called Arithmetica. These texts deal with solving algebraic equations, and have led, in number theory, to the modern notion of Diophantine equation. Earlier traditions discussed above had a direct influence on Muhammad ibn Mazar al-Khwarizmi. He later wrote the compendious book on calculation by completion and balancing, which established algebra as a mathematical discipline that is independent of geometry and arithmetic. The Hellenistic mathematicians Hero of Alexandria and Diophantus, as well as Indian mathematicians such as Brahmagupta, continued the traditions of Egypt and Babylon, though Diophantus' Arithmetica and Brahmagupta's Brahmas Futa Siddhanta are on a higher level. For example, the first complete arithmetic solution to quadratic equations was described by Brahmagupta in his book Brahmas Futa Siddhanta. Later, Arabic and Muslim mathematicians developed algebraic methods to a much higher degree of sophistication. Although Diophantus and the Babylonians used mostly special ad hoc methods to solve equations, al-Khwarizmi's contribution was fundamental. He solved linear and quadratic equations without algebraic symbolism, negative numbers or zero, thus he is to distinguish several types of equations. In the context where algebra is identified with the theory of equations, the Greek mathematician Diophantus has traditionally been known as the father of algebra, but in more recent times there is much debate over whether al-Khwarizmi, who founded the discipline of al-jebr, deserves that title instead. Those who support Diophantus point to the fact that the algebra found in al-jebr is slightly more elementary than the algebra found in Arithmetica, and that Arithmetica is syncopated while al-jebr is fully rhetorical. Those who support al-Khwarizmi point to the fact that he introduced the methods of reduction and balancing, which the term al-jebr originally referred to, and that he gave an exhaustive explanation of solving quadratic equations, supported by geometric proofs, while treating algebra as an independent discipline in its own right. His algebra was also no longer concerned with a series of problems to be resolved, but an exposition which starts with primitive terms in which the combinations must give all possible prototypes for equations, which henceforth explicitly constitute the true object of study. He also studied an equation for its own sake and in a generic manner, insofar as it does not simply emerge in the course of solving a problem, but is specifically called on to define an infinite class of problems. The Persian mathematician Omar Khayyam is credited with identifying the foundations of algebraic geometry and found the general geometric solution of the cubic equation. Another Persian mathematician, Sharif al-Din al-Tazar, found algebraic and numerical solutions to various cases of cubic equations. He also developed the concept of a function. The Indian mathematicians Mahavira and Bhaskara II, the Persian mathematician al-Khayyam, and the Chinese mathematician Zhu Shiji, solved various cases of cubic, quartic, quintic and higher-order polynomial equations using numerical methods. In the 13th century, the solution of a cubic equation by Fibonacci is representative of the beginning of a revival in European algebra. As the Islamic world was declining, the European world was ascending. And it is here that algebra was further developed. History of algebra. From a section Te's work on new algebra at the close of the 16th century was an important step towards modern algebra. In 1637, Rena copyright Descartes published Lagar copyright Omar copyright Try, inventing analytic geometry and introducing modern algebraic notation. Another key event in the further development of algebra was the general algebraic solution of the cubic and quartic equations, developed in the mid-16th century. The idea of a determinant was developed by Japanese mathematician Kawasaki in the 17th century, followed independently by Gottfried Leibniz 10 years later, for the purpose of solving systems of simultaneous linear equations using matrices. Gabriel Cramer also did some work on matrices and determinants in the 18th century. Permutations were studied by Joseph Louis Lagrange in his 1770 paper Ra copyright Flexions sur la Ra copyright solution Alga copyright Brick des copyright Quations devoted to solutions of algebraic equations, in which he introduced Lagrange resolvents. Paolo Ruffini was the first person to develop the theory of permutation groups, and like his predecessors, also in the context of solving algebraic equations. Abstract algebra was developed in the 19th century, deriving from the interest in solving equations, initially focusing on what is now called Galois theory, and on constructibility issues. George Peacock was the founder of axiomatic thinking in arithmetic and algebra. Augustus de Morgan discovered relation algebra in his syllabus of a proposed system of logic. Josiah Willard Gibbs developed an algebra of vectors in three-dimensional space, and Arthur Cayley developed an algebra of matrices. Areas of mathematics with the word algebra in their name. Some areas of mathematics that fall under the classification abstract algebra have the word algebra in their name. Linear algebra is one example. Others do not. Group theory, ring theory, and field theory are examples. In this section, we list some areas of mathematics with the word algebra in the name. Elementary algebra, the part of algebra that is usually taught in elementary courses of mathematics. Abstract algebra, in which algebraic structures such as groups, rings and fields are axiomatically defined and investigated. Linear algebra, in which the specific properties of linear equations, vector spaces and matrices are studied. Commutative algebra, the study of commutative rings. Computer algebra, the implementation of algebraic methods as algorithms and computer programs. Homological algebra, the study of algebraic structures that are fundamental to study topological spaces. Universal algebra, in which properties common to all algebraic structures are studied. Algebraic number theory, in which the properties of numbers are studied from an algebraic point of view. Algebraic geometry, a branch of geometry, in its primitive form specifying curves and surfaces as solutions of polynomial equations. Algebraic combinatorics, in which algebraic methods are used to study combinatorial questions. Many mathematical structures are called algebras, algebra over a field or more generally algebra over a ring. Many classes of algebras over a field or over a ring have a specific name: associative algebra, non-associative algebra, Lie algebra, Hopf algebra, C algebra, symmetric algebra, exterior algebra, tensor algebra. In measure theory, sigma algebra, algebra over a set. In category theory, F algebra and F coalgebra, T algebra. In logic, Relational algebra, a set of finitary relations that is closed under certain operators. Boolean algebra, a structure abstracting the computation with the truth values false and true. See also Boolean algebra. Heading algebra. Elementary algebra. Elementary algebra is the most basic form of algebra. It is taught to students who are presumed to have no knowledge of mathematics beyond the basic principles of arithmetic. In arithmetic, only numbers and their arithmetical operations occur. In algebra, numbers are often represented by symbols called variables. This is useful because it allows the general formulation of arithmetical laws, and thus is the first step to a systematic exploration of the properties of the real number system. It allows the reference to unknown numbers, the formulation of equations and the study of how to solve these. It allows the formulation of functional relationships. Equals 3xa10, where f is the function, and x is the number to which the function is applied. Polynomials. A polynomial is an expression that is the sum of a finite number of non-zero terms, each term consisting of the product of a constant and a finite number of variables raised to whole number powers. For example, x2 plus 2xa3 is a polynomial in the single variable x. A polynomial expression is an expression that may be rewritten as a polynomial, by using commutativity, associativity and distributivity of addition and multiplication. For example, x plus 3, is a polynomial expression, that, properly speaking, is not a polynomial. A polynomial function is a function that is defined by a polynomial, or, equivalently, by a polynomial expression. The two preceding examples define the same polynomial function. Two important and related problems in algebra are the factorization of polynomials, that is, expressing a given polynomial as a product of other polynomials that can not be factored any further, and the computation of polynomial greatest common divisors. The example polynomial above can be factored as x plus 3. A related class of problems is finding algebraic expressions for the roots of a polynomial in a single variable. Teaching algebra. It has been suggested that elementary algebra should be taught as young as 11 years old, though in recent years it is more common for public lessons to begin at the 8th grade level in the United States. Since 1997, Virginia Tech and some other universities have begun using a personalized model of teaching algebra that combines instant feedback from specialized computer software with one-on-one and small group tutoring, which has reduced costs and increased student achievement. Abstract algebra. Abstract algebra extends the familiar concepts found in elementary algebra and arithmetic of numbers to more general concepts. Here are listed fundamental concepts in abstract algebra. Sets. Rather than just considering the different types of numbers, abstract algebra deals with the more general concept of sets, a collection of all objects selected by property specific for the set. All collections of the familiar types of numbers are sets. Other examples of sets include the set of all 2 by 2 matrices, the set of all second-degree polynomials, the set of all two-dimensional vectors in the plane, and the various finite groups such as the cyclic groups, which are the groups of integers modulo n. Set theory is a branch of logic and not technically a branch of algebra. Binary operations. The notion of addition is abstracted to give a binary operation, say. The notion of binary operation is meaningless without the set on which the operation is defined. For two elements A and B in a set S, A, B is another element in the set. This condition is called closure. Addition, subtraction, multiplication, and division can be binary operations when defined on different sets, as are addition and multiplication of matrices, vectors, and polynomials. Identity elements. The numbers 0 and 1 are abstracted to give the notion of an identity element for an operation. 0 is the identity element for addition and 1 is the identity element for multiplication. For a general binary operator, the identity element E must satisfy E equals A and A equals A. This holds for addition as a plus 0 equals A and 0 plus A equals A and multiplication 1 equals A and 1 A equals A. not all sets and operator combinations have an identity element. For example, the set of positive natural numbers has no identity element for addition. Inverse elements, the negative numbers give rise to the concept of inverse elements. For addition, the inverse of A is written AA, and for multiplication the inverse is written or1. A general two-sided inverse element or1 satisfies the property that AA, or1 equals 1 and or1A, A equals 1. Associativity, addition of integers has a property called associativity. That is, the grouping of the numbers to be added does not affect the sum. For example, +4 equals 2 plus. In general, this becomes A, C equals AA. This property is shared by most binary operations, but not subtraction or division or octonian multiplication. Commutativity, addition and multiplication of real numbers are both commutative. That is, the order of the numbers does not affect the result. For example, 2 plus 3 equals 3 plus 2. In general, this becomes AA, B equals BA, A. This property does not hold for all binary operations. For example, matrix multiplication and quaternion multiplication are both non-commutative. Groups. Combining the above concepts gives one of the most important structures in mathematics, a group. A group is a combination of a set S and a single binary operation A, defined in any way you choose, but with the following properties: an identity element E exists, such that for every member A of S, EA, A and AA, E are both identical to A. Every element has an inverse. For every member A of S, there exists a member or1 such that AA, or1 and or1A, A are both identical to the identity element. The operation is associative. If A, B and C are members of S, then A, C is identical to AA. If a group is also commutative, that is, for any two members A and B of S, AA, B is identical to BA, or then the group is said to be abelian. For example, the set of integers under the operation of addition is a group. In this group, the identity element is 0 and the inverse of any element A is its negation, AA. The associativity requirement is met, because for any integers A, B and C, plus C equals A plus, the non-zero rational numbers form a group under multiplication. Here, the identity element is 1, since 1A, A equals AA, 1 equals A for any rational number A. The inverse of A is 1 per R, since AA, 1 per R equals 1. The integers under the multiplication operation, however, do not form a group. This is because, in general, the multiplicative inverse of an integer is not an integer. For example, 4 is an integer, but its multiplicative inverse is a 1/4, which is not an integer. The theory of groups is studied in group theory. A major result in this theory is the classification of finite simple groups, mostly published between about 1955 and 1983, which separates the finite simple groups into roughly 30 basic types. Semigroups, quasigroups, and monoids are structures similar to groups, but more general. They comprise a set in a closed binary operation, but do not necessarily satisfy the other conditions. A semigroup has an associative binary operation, but might not have an identity element. A monoid is a semigroup which does have an identity but might not have an inverse for every element. A quasigroup satisfies a requirement that any element can be turned into any other by either a unique left multiplication or right multiplication. However, the binary operation might not be associative. All groups are monoids, and all monoids are semigroups. Rings and fields. Groups just have one binary operation. To fully explain the behavior of the different types of numbers, structures with two operators need to be studied. The most important of these are rings and fields. A ring has two binary operations and, with a, distributive over plus. Under the first operator it forms an abelian group. Under the second operator it is associative, but it does not need to have identity, or inverse, so division is not required. The additive identity element is written as 0 and the additive inverse of A is written as AA. Distributivity generalizes the distributive law for numbers, and specifies the order in which the operators should be applied. For the integers a, c equals a, c plus ba, c and ca, equals ca, a plus ca, b, and a, is said to be distributive over plus. The integers are an example of a ring. The integers have additional properties which make it an integral domain. A field is a ring with the additional property that all the elements excluding 0 form an abelian group under A. The multiplicative identity is written as 1 and the multiplicative inverse of A is written as or1. The rational numbers, the real numbers and the complex numbers are all examples of fields. See also Outline of algebra, Outline of linear algebra, Notes. References, Boyer, Carl B., A History of Mathematics, John Wiley & Sons, Incorporated, ISBN A0-471-54397-7 Donald R. Hill, Islamic Science and Engineering. Ziauddin Sadr, Jerry Ravitz, and Boron van Loon, Introducing Mathematics. George G. Verghese Joseph, The Crest of the Peacock, Non-European Roots of Mathematics. John J. O'Connor and Edmund F. Robertson, History Topics, Algebra Index. In Makshita History of Mathematics Archive. I. N. Herstein, Topics in Algebra. ISBN 0-471-02371-X, RBJ.T. Allenby, Rings, Fields and Groups. ISBN 0-340-54440-6, L. Euler, Elements of Algebra, ISBN 978-1-899618-73-6, Asimov, Isaac. Realm of Algebra. Horton Mifflin, External Links, Khan Academy, Conceptual Videos and Worked Examples, Khan Academy, Origins of Algebra, Free Online Micro-Lectures, algebrarules.com, an open-source resource for learning the fundamentals of algebra, 4,000 Years of Algebra, lecture by Robin Wilson, at Gresham College, October 17, 2007. Algebra entry by Vaughan Pratt in the Stanford Encyclopedia of Philosophy.